I'm Debasis Mitra, host of today's seminar. We are privileged to have Peter Shor, a pioneer in algorithms for quantum computing, speak to us on quantum money. So I'll be brief in my introduction on the assumption that you've read his bio and touch on only a few highlights. Peter was a medalist at the national and international math Olympiads at the age of 18. By the way, I should mention, he just confirmed he was born in New York City. His bachelor's is from Caltech, and his PhD from MIT is in applied mathematics. After a year as a postdoc at Berkeley, Peter joined the Math Center at Bell Labs in Murray Hill, New Jersey in 1987. He was about 28 years old then. He did his work there on what we have come to know as Shor's algorithm for factoring on a quantum computer. He went on to work on error correction and fault-tolerant quantum computing, which remain his interests today. He left for MIT in 2003 as Morss Professor of Applied Mathematics, which is what he is today. I'll only mention a small selection of his many prizes and awards. These include the Nevanlinna Prize, the Gödel Prize, and the Dirac Medal. He's a member of the National Academy of Engineers and the National Academy of Sciences. Let me move on. Please use the chat box below on the bottom of your Zoom screen to write in your questions during the lecture and on conclusion for Peter to answer. You will see the chat box at the bottom of the Zoom screen. By the way, the recording will be available and you'll be informed. Thank you. Peter, it's all yours.
Okay. Let's see. I opened the chat box to look at it, and now it's in the middle of the screen. And okay, I'm set. So I'm going to be talking about quantum money and what is quantum. Okay, come on. What is? There we are. And there are my grants. And what is this little red line here? There's some way to get rid of it. So outline of my talk is, thank you. I'm going to start off by talking about the motivation for quantum money and the history of quantum money, and then some of the cryptography background that goes into quantum money. And then I'll go over, I guess, 3 proposals for quantum money. At a very high level. First is quantum money from knots, which I will sketch how it works. Then I'll talk about quantum money from modular forms. And since I don't really understand enough abstract algebra to know how that works, I'll give a very, very brief sketch. And finally, I will talk about quantum money from lattices, which is the new result, which I have just finished writing up, and I should post on the archive in the next week or so. And that's the thing. So what is quantum money? Well, it's basically a cryptographic protocol. You have 2 players. One is a mint, which can create quantum states, and you want these quantum states so that they can be verified. That means each quantum money state has a serial number. So a quantum money state is actually a state of a quantum system. So it's not classical. You need qubits. So it lives on a quantum computer, which maybe is an ion trap, or maybe it's superconducting circuits in silicon. And what you want the quantum money to satisfy is that, one, the state can be verified. So looking at the serial number tells you a quantum algorithm which will verify it. And so if it's a valid quantum state, the verification procedure should pass it almost all the time. And second, it cannot be duplicated, which means even holding the quantum money state and knowing the verification procedure, someone who wants to counterfeit the quantum money cannot make two states that both pass the verification test. And, if real money worked like this, it would be ideal because it would be uncounterfeitable. So, of course, the problem with money is that you can make copies, and the nice thing about quantum states satisfy is that there's a no cloning theorem, which says you cannot make a copy of an unknown quantum state. So for the quantum money, you do not know how to prepare the state. You know enough about it to verify it, but you cannot make copies. So the no cloning theorem, you'd think this would immediately let us use quantum states for money. And aside from the fact that quantum states only last for a few minutes on a very expensive quantum computer. But this was Wiesner's idea in 1969, and he came up with a scheme for quantum money that I'm going to tell you about in a little bit, but it had a bunch of drawbacks. And we'd like a quantum money scheme that doesn't have all the severe drawbacks. So what do we really need for quantum? Oh, wait, what is going on here? Why can I not go backwards? Oh, there we go. Good. So for many things, quantum cryptography was done with ad hoc crypto systems. So this is the cryptography background you need to understand for the talk, many of which were eventually broken. Over the last half century, cryptography has become much more mathematical, and now theoretical computer scientists try to prove the security of crypto systems as much as they can. And there are two kinds of security proofs in cryptography. There's security through information and security through complexity. So security through information, what you have to know is that no matter how powerful a computer your adversary has, you have to show that they will not be able to break the crypto system because they don't have enough access to the information in the message. And the reason that we don't use informationally secure crypto systems is that there are virtually no crypto systems that are informationally secure. The one we know is one-time pad, which also has other big drawbacks. And the secure, computationally secure, means the security of the crypto system relies on the difficulty of solving some computationally hard problem. So for quantum computation, the background you need to know is that quantum states can be represented as unit vectors in an n-dimensional complex vector space. And a qubit is a two-state system, which means it's a vector in a two-dimensional vector space. So we're going to let the basis states be 0 and 1, even though in real life they'd be, clockwise or counterclockwise flow of circuit in a superconducting transistor, or maybe the ground state and the excited state of an ion in an ion trap. And with n qubits, you have 2 to the n dimensional vector space. The basis states are just n-bit binary strings. And transformations on quantum states are given by unitary matrices, which preserve the lengths of the vectors so that they take unit vectors to unit vectors. So our original motivation, or my original motivation for quantum money, was we asked whether there are tasks which can be done with computational security on quantum computers, but not classical computers. There's this very famous quantum key distribution system, which is informationally secure, which means you cannot break it unless you manage to circumvent the laws of physics. But classically, there are lots of crypto systems which are computationally secure, and we were wondering if there were any new tasks that can be done on quantum computers with computational security. And one such possible task was unduplicatable states, which is really quantum money. So the first proposed quantum money was by Stephen Wiesner in 1969. And here is Charlie Bennett's representation of a bill of Stephen Wiesner. There are a bunch of qubits, which are in one of the states, up, down, left diagonal, or right diagonal. And these, you can think of them as polarizations. And now, if you knew the state was one of these two, you could copy it. And if you knew the state was one of these two, you could copy it. But if you have all four things, then by the Heisenberg uncertainty principle, if you measure the state, you're going to disturb it. So if you get the information about whether it's this one or this one, you've completely lost the information about whether it's left diagonal or right diagonal. And so anybody who does not know the polarizations of these states cannot copy them. So if somebody tries to measure them, they will disturb any states and the diagonal basis, and they try to measure them in diagonal basis, they'll disturb them in the orthogonal basis. And if they measure them in an in-between basis, they will have a small chance of disturbing all of them. So that means that this is uncopyable unless you know the basis of the states. And if you get such a bill, you can send it to the bank and they can verify that it was indeed the right bill, and then you get the money. Of course, if you're a merchant, you want to be able to verify that the bill is legitimate without sending it back to the bank. And the problem with it is if the bank gives this information to the merchant, then they can counterfeit the bill. And if it gives some of the information to a whole bunch of merchants, these merchants can, get together and collude to copy the bill, counterfeit the bill. So that's the problem with Wiesner's money. And the question is, can we find a quantum money protocol without this drawback? So I'm not going to explain the protocol based on non-invariance. I'm going to explain a very similar protocol that doesn't work at all, but will tell you how the non-invariant protocol works. So this is based on graph isomorphism. So the background on graph isomorphism, two graphs are isomorphic if you can relabel the vertices of one to yield the other. So these are two isomorphic graphs. And there's no polynomial time known for graph isomorphism. So now suppose you could counterfeit the money. Well, now suppose you could take a graph G1 and create the state 1 over root n factorial, the superposition of all possible isomorphic copies of this graph. Then we can solve graph isomorphism. How? Suppose we're given graphs G1 and G2. What we do is we pair the state, the superposition of all graphs G1 and the superposition of all isomorphic copies of G2. And now, if the two graphs are isomorphic, these states are equal. And if they're not isomorphic, they are orthogonal. So what that means is that this state is the +1 eigenstate of the swap operator. So he can measure this and see if this state really is in the +1 state. So if we could measure it, the state, if we could make the state, then we could tell whether two graphs were isomorphic. So the moral of the story is, assuming that graph isomorphism is hard, we cannot create the superposition of isomorphic copies in a given graph. Now let's consider the following algorithm for creating a quantum money state. The mint starts with the equal superpositions of all graphs, and that's easy to create because you put each edge in a superposition of present or absent. Now you measure some property of graphs which is invariant under permutation of the vertices. So let's say it's a spectrum. Then if the spectrum is S, you're in the superposition of all graphs which have the same spectrum. And if there aren't that many graphs with the same spectrum, you're essentially in the superposition of all the copies, all the isomorphisms of one graph. And we know that's hard to create. So you can ask, can we verify the state? So the quantum money is a superposition of all copies of all isomorphic copies of all graphs with a given spectrum. So how when we test it? You see that if we're really in that state. To test it, we check that the spectrum of G is indeed S, and that the state is invariant under random permutations of the vertices, because this is the superposition of all copies of G, it's invariant. And it seems really hard to create a state that passes these tests without being able to solve graph isomorphism. So that was, one of our first ideas for quantum money, and it doesn't work. Why doesn't it work? Well, it's because graph isomorphism turns out to be easy for random graphs. And the way we've constructed the quantum money, we get a random graph. So how do we fix this? Well, what we do is we use the same idea, and we throw out the quantum, we throw out the graphs and the isomorphisms and try to come up with some mathematical system which works more or less the same way, but where a random, it's not easy to do isomorphism for random graphs. So have we done this? Well, I think the verdict is still out, but what we're going to do is, instead of using graphs, we're going to use grid diagrams of knots. And this is a grid diagram of a knot. You see there are, this is an n by n square, and you have one permutation of the vertices that you color red, and another permutation of the things. So one from each row and one from each column, you color blue, and you connect the blue dots to the red dots in the same row and column, and columns go over rows. So that's a grid diagram. You can represent any knot by a grid diagram. And now, instead of random permutations, you use random grid Reidemeister moves. And what are those? Well, one of them is taking these two vertices and moving them under the entire grid diagram to the leftmost column. Another one is, we don't have any good examples of the second one, but the second one is basically, if you have a loop that goes over an edge, you can move it across the edge, so to get rid of two crossings. And the third one is, instead of replace a vertex by a little loop, or vice versa. And you can get any knot this way by starting, or any equivalent. So if you have a knot that's represented by a grid diagram, you can get any grid diagram that represents the same knot by doing these random grid Reidemeister moves. And you're never going to get anything but the same knot. So these correspond to the permutations of the vertices in graph isomorphism. And we place the graph invariant by some polynomial time computable knot invariant, and there are lots of those. And for example, one of them is the Alexander polynomial. And so you can ask, is this knot money protocol secure? And we don't know. Nobody has ever looked at this problem. But I can say that even if we could solve knot isomorphism in polynomial time for a random knot, This wouldn't break the knot money protocol because for knots, unlike for graph isomorphism, it's not enough to create an equal superposition. Knowing how to solve knot isomorphism is not enough to create an equal superposition of all grid diagrams of a given knot. And that's what we need to break the knot money scheme. Okay. The next thing I'm going to be talking about is quantum money from modular forms. So again, I don't know much about modular forms, but they're connected with elliptic curves, and Daniel Kane has proposed a quantum money protocol based on modular forms. And this is an example of a diagram of a modular form. It's basically a lot of semicircles in the upper complex plane. So here's the basic idea in terms of quantum mechanics. In quantum mechanics, if you have commuting unitary operators, you can measure all their eigenvalues simultaneously. And when you measure it, you will get a random eigenvalue for each of these commuting unitary operators. And the quantum state will become the associated eigenvector for this set of eigenvalues. So the idea is that the serial number for the money is a set of eigenvalues. And if you measure the same state again after you measured the first time, you will get the same eigenvalues. So this means that this is good as a money state. And the reason that you can create this money is you start with a random state, and you measure all these commuting unitary operators. You will get some set of eigenvalues, and now the state will have an eigenvector in the right eigenspace, and you use it for the money. And if you started with the same random state, and you measured all these commuting unitary operators, you would get a different set of eigenvalues. So you can't possibly get two bills with the same serial number. So the question is there some other way where you can get the, given the eigenvalues and given one eigenvector in that eigenspace, is there some way you can get two eigenvectors from that eigenspace? And nobody knows how for Daniel Kane's money scheme. And if you abstract this idea to treat eigenvectors and eigenvalues as a black box, you can prove that this is secure. But of course, to have a real quantum money scheme, you need a non-black box that implements this securely. And Kane proposes using Hecke operators on modular forms. And again, I don't know if anybody has really looked at this quantum money proposal seriously to find whether it's secure. Okay. So now we come up to the new work. So this is a quantum money protocol that is based on short vectors and lattices. So I don't know if you've heard about, the post-quantum cryptography, but the two widely known public key crypto systems are based on discrete logs and are based on factoring. And those both are vulnerable to attacks with quantum computers. So people looked around for different public key crypto systems that were not based on attacks by quantum computers. And there was Macaleese crypto system, and a very closely related crypto system based on high dimensional lattices. And since then, people have really, worked on improving the lattice crypto systems. And Oded Regev said, came up with a problem learning with errors, which is widely believed to be hard even for quantum computers. And so now everyone is trying to base their cryptographic protocols on the problem of learning with errors. And I'm not going to go into learning with errors, what learning with errors is, but I'm going to go to a problem which is, probably just as hard, which is finding a short basis of a lattice. So what is a lattice? Well, a lattice is just a set of integer combinations of n vectors in n dimensions. So you take n vectors in n dimensions, and you look at all possible integer combinations of them, and they will form a grid or a lattice or something that fills up all the n dimensions. And the hard problem is, given a basis of long vectors, find a basis of short vectors. So I don't know if you can see these two blue vectors, but the idea is these two blue vectors are supposed to represent a basis which has long vectors in it. And here are the two shortest vectors in the lattice, and they form a basis as well. And now the question is going from these two vectors to these two vectors. And that's really easy in low dimensions. So in 2 dimensions, it's essentially nearly trivial, but in high dimensions, it's a hard problem. And of course, I can't demonstrate this because I can't draw high dimensions on a slide. But the best known algorithm finds a basis that's exponentially longer than the shortest possible basis, exponential in n. And what we're going to assume is that you cannot find a basis that's only polynomially longer than the shortest possible basis. Okay. So consider lattice dimensions. So we're going to use a subclass of lattices, which is just as hard as any lattice. So consider lattices in n dimensions that lie on a p to the n cube of integers. So the lattice, so all the lattice points are in this cube, or equivalently, you can consider the whole space to be filled with copies of this cube, and the lattice is periodic with period p in every dimension. And we're also going to look at such lattices where there's exactly one lattice vector in every hypercolumn. So there's one lattice vector along this red line, for example, and one lattice vector along, another line that extends from the top to the bottom. So in P, so there are P to the n different lattice vectors in this cube, and there are P to the n minus, well, there are P to the n different vectors in the cube, and there are P to the n minus 1 lattice vectors in the cube. And if the short vector problem is hard for any lattices, then we can show it's hard for this class of lattices. Now, next thing is the dual lattices. The dual of a lattice is a set of all vectors which are perpendicular to all the vectors in a lattice. And here, what we're going to do is we're going to say a vector is perpendicular to another vector if their inner product is a multiple of p. And this, this scales the dual so that the dual lies in the same p to the n cube of integers. And the dual of this class of lattices has exactly one lattice vector in each hyperplane of the p to the n cube. So it turns out that the dual lattice is much sparser than the original lattice. Okay, so now what we want to do is define the quantum Fourier transform that operates on vectors in this lattice. And I'm not going to go into all the details of the quantum Fourier transform and not into how you can actually achieve it in polynomial time, but I'll tell you what it does. What the quantum Fourier transform does is it takes a Gaussian superposition of vectors around the origin to a Gaussian superposition around each of the points of the dual lattice. So these are the points of the dual lattice. The points of the original lattice in this diagram are very, very dense, so you can't really see them. But this is a Gaussian superposition of all of vectors around the origin, and that means that each vector has an amplitude on it in the quantum Gaussian superposition state, which is a Gaussian, and it falls off exponentially if you as you go away from the origin. And another nice thing about the quantum Fourier transform, if the Gaussian superposition around the origin is large, then the Gaussian superposition around each of the dual lattice points is small, and vice versa. If the Gaussian superposition around vectors has a small standard deviation around the origin, then the Gaussian superposition around each of the vectors of the dual lattice has a large standard deviation. So what I'm going to do first is tell you a quantum algorithm that doesn't work. So to create the quantum money state, what we're going to do is we're going to create a large quantum Gaussian ball at 0. And then we take the Fourier transform of it. And then we find the closest lattice point. Now, there's something I should tell you here. In general, if you have a vector, finding the closest point in the dual lattice is a hard problem. But if your vector is very close to the dual lattice, you can do it. And in fact, if it's exponentially closer than the shortest distance between lattice points, then there's a polynomial time algorithm for finding the closest dual lattice point. So what we do is we make these Gaussian ball around the origin large enough so that all of these states have a very small, are very close to their dual lattice. And then we can measure the lattice point that's close. Dual lattice points is closer to a given point here. And if we measure that, what's left is just all the lattice points around this dual lattice point and a very small Gaussian superposition. And that is going to be our quantum money state. And again, this is the first attempt at our algorithm, and it didn't work. Okay. So to create the quantum money state, we take the large Gaussian ball at 0, we take the Fourier transform, and we measure the nearest dual lattice point to get a dual lattice point W. So why shouldn't you be able to copy this? Well, suppose you could copy. Now you have a small Gaussian ball around the original, around the dual lattice, this dual lattice point, and another copy of this. Oh, and I forgot to say something. What is the serial number? The serial number is this dual lattice point, which all these points are near to. So suppose you could copy, then you would have you would have 2 copies of this Gaussian ball. You can take a sample from this one, you can take a sample from this one, and you can subtract them. And when you subtract them, you get a lattice vector which is close. And since V1 and V2, the points you're subtracting, are both close to this dual vector W, then V1 minus V2 is close to 0. So if you could copy this state exactly, you could sample a point from each of these copies and get a short vector. So our first quantum algorithm doesn't work. So what was the idea behind verifying it? First, check that it's a superposition of lattice points near W. Well, that's easy to do. You just can ask, are you very close to W, to the lattice points. And since all of them are, they will all say yes. And because they all give you the same answer, then you're left in the superposition of lattice points near W. Okay. Now, the other thing you can do is you can take the Fourier transform to get big balls around each lattice point. So now the idea is, suppose you shift these big balls by some translate, by some vector and you want this vector to have non-zero overlap of the balls, but also you don't want these balls to overlap totally. And now you can measure this overlap by doing a swap test. So you can check that this superposition of all the big balls, really, all these balls are the right size and they are big balls around each lattice point. So you think that lets you not verify the thing. But then what we realized is okay, there's an extra period and sentence here, which I must have introduced somehow. The swap test we need to use is linear, so it can't distinguish between a superposition round of Gaussian ball, of point states around a Gaussian ball, and a mixture of states. So what can an inspiring counterfeiter do? He could just sample one quantum vector from the quantum money state, which we call was a set of vectors which are all very near to this dual money state, or dual lattice vector W. Okay, I went too far. And then he could duplicate it, because now it's just a single state, a single lattice vector, so it's a classical thing. And you can duplicate classical information as much as you want. And, it's not just the swap test that can't distinguish between a superposition of states around the small Gaussian ball and a mixture of those states. It turns out that we've tried a whole bunch of different tests and none of them work to make this distinction that we can, that we need to make this quantum money work. So I think this is something very interesting about lattices. If you have two points that are both near some dual vector, you can't, or rather, if you have a superposition of states near a dual vector or a single state near that dual vector, there's no way to actually tell them apart. So how do you fix it? Well, the only way we figured out how to fix it is to use two copies of the Gaussian ball around the lattice vector W. So why does this work? Well, if you use two copies, the swap test is quadratic rather than linear. And that means you can tell superpositions and mixtures apart. So there's a general theorem that, you have you have a superposition of things and you use the swap test to check, what the overlap is. Well, if under certain conditions, if you measure them and then use the swap test, the first result with a superposition is always less than the expected value we'll get with the second result with the mixture of states after you've measured them. So now this will tell them things apart. And in fact, for this, so with the quantum money, well, now we have two copies of the Gaussian ball around the lattice vector W. So you can measure both of them. And get one short vector. But to counterfeit this quantum money, you really need to get a whole Gaussian superposition of points around this dual lattice vector. And for that, it appears you need an entire basis of n short vectors rather than just one single vector. So with quantum money, this looks like it's might be secure. And what do these calculations do? Well, in the real quantum money, you have two Gaussian balls, which have a standard deviation. And let's call them sigma, although, I mean, really their standard deviation is some complicated expression. And they're offset by some vector t. Well, I should say the square of the overlap of these two balls, which is what you measure, is e to the minus 1 over 8 t over sigma squared. So if the offset is very small, then this is essentially 1. And if the offset is large, it goes to 0. So what do you get if you measure a single vector and then do the same swap test? Well, if you measure a single vector and do the same swap test, what you get is a plane wave, which is represented by something like e to the minus 2 pi I x dot b over p. And now, if you have this plane wave, actually, this is the amplitude on vector x. Now, if you take this plane wave and shift it by t, all you've done is you've multiplied it by some complex phase. And now you take the square of the overlap, you get 1. So this guy is much smaller than this guy, so you can test them in your with your quantum computer. So this money seems to work. So what are the disadvantages of the corrected protocol? Well, in our original protocol, the mint didn't need to have any secret information to create the money. You know, it created the money and it was random because we measured a random dual lattice vector. Here, well, the mint can measure one random dual lattice vector, but now it needs to create a Gaussian ball around this different dual lattice vector. And to do this, what it needs is to know a basis of short vectors for the lattice. So to get, you can find random lattices with a basis of short vectors, essentially by, taking these basis and then generating the lattice. So you can do this, but the mint now needs to know information, which means it can create as many copies of the money with the same serial number. Okay. And one of the nice things about the original not isomorphism money and Keynes modular forms money is that in those quantum money schemes, the mint can only create one copy of a quantum money state with a given serial number, because they create the quantum money state by measuring something random, which I guess in the quantum isomorph in the knot money is they get a random knot. In the modular form money, they get a random set of eigenvalues for these commuting operators. And there's no way they can make the same measurement and get the same result again, because quantum measurements give random results in most, for most things you're measuring. So that is one disadvantage. And the next thing I need to tell you is that the swap test isn't deterministic. wait, what am I saying? Yeah, the swap test isn't deterministic. If the state have some overlap, which is not one, then when you perform the swap test, you will get one probability of seeing yes and another probability of saying no, and you determine the amount of overlap by taking the probability that it answers yes and then doing a calculation from that. So if we just had one superposition of lattice vector states, then measuring the quantum money would destroy it. So in order for the quantum money state not to be destroyed by a successful verification test, it needs to test the verification test with probability 1 minus epsilon for a very, very small epsilon. And how we do this is we make the real quantum money state be many, many, many copies of, well, different quantum money states that we've described so far. And we say that it's verified if, the number of quantum money states that pass the test exceeds some threshold. And we choose the threshold so that it's very small. The probability that fake money state will pass, or the probability that a real money state will fail, is very, very small. And now we can succeed in having quantum money that does not get destroyed by testing. Okay. So I guess that was, I'm ending like 5 minutes earlier than I thought I would. So maybe I should open this. Are there any questions? Let's see. Question is, how many logical qubits would you need to create a quantum money printing system? Well, it's going to be a lot, because first you need these lattice states in high dimensions, and high dimensions, let's see. I haven't figured this out, and I don't really know how big your lattices need to be to actually work, but I guess, maybe 100 digits would be big enough. So that's 200 qubits. And then you need to have one of these, and then you need to have many, many of these different lattice money systems to get your statistical independent samples, so that you answer the question either almost always yes or almost always no, and that you're probably going to need another few hundred at least. So that's probably going to be up in the tens of thousands. But as I say, I don't really know, because I haven't looked into how large these lattices need to be so that they can't be broken by classical cryptography.
So Peter,
how much time?
Peter, maybe I just mentioned for the benefit of those who entered late that, yeah, please feel free to write your questions down on the chat box, which you'll see at the bottom of your screen. And as you can see, Peter's responding to them one by one. Thank you. Go ahead. There's a question from Al.
Oh, another question is, how much time would be required to make a purchase with your quantum money? Well, I mean, everything you need to check is fairly straightforward, so it should not, So I don't know how much time it is. That's another thing we haven't figured out. But if you have a few hundred copies of this quantum money state, and each of them is a few hundred digits, it probably wouldn't be more than 1 million operations. And that is undoubtedly too undoubtedly fairly long time, but really the bottleneck is going to be the number of logical qubits. Okay, lots more. Okay. So what will make quantum money practical? Well, really, I think we need to come up with better quantum money schemes to make it practical. But there's really no reason that these quantum money schemes have to be so computationally expensive. So now, yeah, I think it's quite possible someone will come up with a better one soon. Quantum money seems to be an extension of quantum cryptography. Is this true? Well, quantum money is definitely, it's a cryptographic protocol that uses quantum mechanics. So it's an extension of quantum cryptography in that way. Are there any applications of this quantum money protocol regarding encryption or key distribution? I wish I knew. I haven't found any. Okay. And here we are. In the current current monetary system, people game the system by taking advantage of the noise in the system. A day trader, well, it's not day traders that make the money. It's these very large venture capital firms who are gaming the system, and the day traders are just losing. But yeah. Is there any way to game the system and make money fraudulently with quantum money? Well, I don't know. One fraudulent thing that I don't see how to do it is I give you a quantum bill and you say, no, come on, this bill is counterfeit. And of course, because you've had it in your possession, you can replace it with an actual counterfeit quantum bill. So, but you could do this with regular money too. So, but I don't really see any good way to do this without some kind of interactive protocol. And if you have an interactive protocol, maybe you could use classical cryptography with interactive protocols for some kind of classical digital money. Okay, so I have some future work things here. Are there other cryptographic protocols that could use quantum money protocol as a subroutine? That was one of the questions in chat. Are there other ideas? Are the ideas from our quantum money useful for other protocols? Well, I don't know. Lattices are certainly very, much in demand as a source of post-quantum cryptography. And this idea that if you have a lattice, you cannot tell a superposition of vectors around close to a lattice point from just a random vector in a lattice point is very intriguing to me. I wish I could try to find some way of proving that, or at least proving that given other assumptions. And I wish I could find some use for this idea. So are there other quantum cryptographic protocols that can be implemented using lattices? Well, people are already coming up with them. And our current protocol uses massive numbers of qubits. Can you find a more economical protocol? And I guess this is the small Gaussian superposition of vectors around a dual lattice vector seems to have the collapsing property. And what that means is that you cannot tell a single vector from the superposition, from the whole superposition. So can you use this for any cryptographic purposes? And you can say, well, this is our quantum state. Is there a quantum state which is essentially a zero knowledge proof? So our quantum state, reveals whoever prepared it no short basis for a lattice. but it doesn't reveal, it only reveals one short lattice vector, whereas to have a short basis for a lattice, you need n short lattice vectors. So there's a gap between how much the creator of the quantum state needs to know and how much the recipient of the quantum state can obtain from it. But we would like something that where the recipient can get zero information out. So we'd like the quantum state that somebody who knows a short basis for a lattice can prepare, and then somebody else can check and say, yeah, that guy knew the short basis for a lattice, but it doesn't reveal any short lattice vectors. And there are zero knowledge protocols that do this classically, but they involve interaction between the two participants. So this question is there a single quantum state that reveals that the recipient knew something that they needed to know to prepare it, but it doesn't reveal any information beyond that to the person who has it. Okay, so thank you.
Peter, before, there's one other question that came in from JD Walk. It's there. Can you see it?
Let me look.
Wanted to read it?
Yeah, I mean, I'm reading it, but I'm not really. Ray other protocols seems quite interesting applications as tokens in nuclear release, permission action links. I don't really understand that.
Yeah.
Yeah, what derivative products would be incorporated using this quantum money system? Well, I mean, if you have a complicated quantum cryptographic protocol, you could use this as a proof of identity that, person A knows the short basis for this lattice. So now person A can reveal that they are actually person A and not someone masquerading this as by giving person B this quantum money. And so that would, be a proof of identity in a more complicated quantum cryptographic protocol. And I haven't thought of any other good things that you could implement using this.
So Peter, you want to hazard a guess when it might come to reality, quantum money, and what are in other words, would you like to look into the engineering part of this and say how feasible or when it might be feasible?
Okay, so I mean, I think it's very likely that quantum money schemes will be invented that use many fewer qubits, and if we invent one of those schemes, then we will actually have if we invent one of those quantum money schemes, then it will bring the actual implementation of quantum money much closer to the present than with any of the current quantum money schemes. So I think we just have to wait for some clever person to come up with a better quantum money scheme. I mean, this one, if you assume that it's going to take 10,000 qubits, 10,000 logical qubits to implement, that's not going to happen until, you have quantum computers with enough memory to factor large numbers. And that's, probably at least, I guess that's at least 30 years away. But that's a wild guess.
Well, still very interesting. Okay, there's another question from Tiaga Nandagopal. Is partial verification of states a way to reduce the complexity of implementation of the system? Partial verification of states.
Yeah. So Yeah, if you don't, well, I mean, I mean, if you reduce the money, I mean, if you use the system currently to be small enough that somebody could actually break it with a classical computer, that's not really going to work very well. What you'd like to do is have some a smaller probability of breaking it quantumly, but still resistant to classical computation. And I mean, the problem with, making it looser in terms of the probability of guessing it is that, every time you use it, if you have fewer copies of this money, then the money will degrade slightly. And so there's a balance between how much the money degrades, so how many times it can be used, and its size. Okay.
So you've never written down any of your thoughts on this, the practical looking ahead?
No, I haven't. I mean, so far I've written this paper as a purely theoretical construction. Actually, I know the first thing you should do to make it practical, to try to make it practical, is to use this construction of Watrous to try to reduce the number of different copies of states you need. And I guess the next thing I should do is try to figure out whether this actually works. And if it does, you will only need a few copies of the quantum money state rather than many, many, many copies of them. Okay.
Well, Peter, as somebody said here, I guess it's Tiago, great talk. Look, there's a very large number of people still around. So thank you very much. Thanks very much. I appreciate it. And
yeah,
we don't have to wait this many years before I see you again.
Okay, I hope not. It was, how long has it been? Nearly 20, I think.
Yeah.
Okay.
Thank you very much.